Okay, getting back going here with the June 2016 exam, Geometry, Common Core Regents. So we've got this construction problem. Um, let's see. So we've got to. I'll talk about what we have to do, and then I'll have to go over to the other software, Geometry Sketchpad, to do this. I just can't show what my compass tool is doing here. We need to construct a tangent line, and a radius and a tangent, or a diameter and a tangent, at that point of tangency A. Okay, so if we do this properly, it's going to make a right angle. A tangent and a radius are always perpendicular. They're going to form a right angle there. So basically the construction we've got to perform here is we've got to go perpendicular through a given point. So I'm sure you've seen videos on that. That's what you got to go look for. So the point that we're going to be through is A, and we're going to be perpendicular to OA. So perpendicular to OA through point A. All right, now what it's going to look like, here's what I'm going to attempt to show you over there on the Geometry Sketchpad. Okay, whoops. We'll get rid of this right now. What I'm going to attempt to show you is I'm going to take a compass tool and put the center on A and draw this arc, or a full circle. And then what I'm going to do is I'm going to take my straight edge and form a straight line. I'm going to come up with another point. I'll just call it B. Now, O to A is going to be the same as O to B. So then what I'm going to do is I'm going to construct the perpendicular bisector of OB. What that's going to do is, of course, go through A, because A is exactly between O and B, and then it's going to get me perpendicular. So that's my concept. To start off, I needed this arc right here to create point B, which is the same distance from A as O is. All right, so let's go over and do that over on Geometry Sketchpad. So, all right, starting out with that first concept there, I'm going to center my compass tool to make a circle centered at A with a radius opened up to B. Okay, and what we'll do, since that's, I'm going to just make that, dashed. Okay, so you've got to leave this. That's your work shown. Now we're going to construct a line. Just use your straight edge. Okay, so this is the point I was talking about, B, over on the other diagram. So now we'll label that. All right, so now we've got that labeled. So B to A is the same as O to B. All right, now we'll construct perpendicular bisectors of those. All right, it's going to get pretty messy, but I'm going to pick a random point out here. So this is going to be my radius. Okay, so what's going to happen is it's going to be more than halfway. It's just a random spot on my compass tool that's more than halfway between O and B. All right, so I'm going to construct that. We'll get rid of this in a second here. I'm going to use the same distance from B. Okay, it doesn't look as nice here, but what we end up having, if we can focus on these two here, is those are the two circles I just made, centered at B and O. Same radius was used. Okay, so those are going to create 2 points that are the same distance from O and B. Now if I connect those, and I will make it, there it is. That's the tangent line we're looking for. You can see that it's through A, and it will be perpendicular to OA. All right, so let's get back over here. That's basically what I wanted to show you for that construction. All right, so we'll move on back to over here. That's okay, so now we have a cylinder that we're going to get number of gallons of fuel. Okay, looks like combination of volume and density here. All right, so let's use this information. Let's write it down. It's going to be 231 inches cubic inches is in 1 gallon. Okay, so this is a conversion that we're going to use later on. Um, let's see, diameter. All right, so what we have is do the best you can here. Drawing your cylinder. We've got a diameter of 22.5. All right, so if that's the diameter, we're going to need the radius. You're going to divide by 2. All right. Next, there's a height of 33.5 inches. Perfect. So for a cylinder, our formula is pi r squared h. It's right on the formula sheet. So pi times 11.25 squared. Be really careful there. Don't use the 22.5 times the height of 33.5. All right. So go ahead and let the calculator find that for you. You're going to get 100 or 13,319.9. Okay, that's your volume, and that's going to be in cubic inches. Just check that. They gave us the measurements in inches, so that is going to be cubic inches. You squared the radius, so that gives you inches squared, times the height gives you inches cubed, three-dimensional. All right, now we've got to convert that to gallons of fuel. And I guess we're assuming it's full. Yeah, it doesn't seem like, okay, so it's full, apparently. So what we're going to get is how many gallons. What I would do is, I like proportions here, and I use something that science uses, which is a careful attention to units of measure. So the cubic inches, if you decide to put it on top, that's fine, and gallons underneath. Okay. We'll do the same thing over here. We don't have the gallons, so that's X, and there's a volume of 13,319.9 inches cubed. So that helps us set up a proportion if we pay attention to units of measure. So now we'll cross multiply. We won't bring the units of measure along, but we could. Okay, and then 1 times that's going to be 13,319.9. And basically, the only reason I did this was to be certain the operation I was going to use. All right. You know, it's hard to tell whether you're going to multiply or divide. Most of the time, you can guess correctly, but this process gives you a sure method. All right, so that's going to be 57.661. All right, and it says nearest tenth, that's 1 decimal place. So we're going to have to say 57.7 gallons. Okay. All right, prove. All right, we just want to prove that they're similar. We're given parallelogram. All right. So here's what I'm seeing. We've got there's no side measurements, so it looks like it's going to be an angle-angle similarity proof. Easiest one to work with is the vertical angles. Since this is a parallelogram, I'm looking for this right here. Now I tell my students, look for the N or the Z or backwards N, backwards Z. And when you go to the inside corner of this, we've got alternate interior angles. So there's my N, those inside corners right there. Okay, those are going to give me congruent angles by alternate interior angles. So that's going to be my process. All right, start off number 1. I'm going to start off with, let's go right to the vertical angles. Get those out of the way. So angle DFE is congruent to angle BFG by vertical angles theorem. Oops. Or you could say vertical angles are congruent. All right. Now it's going to take a few steps to get those other angles. So let's start out with the fact that ABCD is a parallelogram, because we're going to use that. So we've got to mention it in our proof. And then the conclusion from that is, we'll say AD is parallel to CB. And that's because opposite sides of a parallelogram are parallel. Make sure this coordinates with what you're saying, right? There's other properties of opposite sides of a parallelogram, but we need the parallel. So now we're going to go with angle EDF. Angle EDF is congruent to angle GBF by alternate interior angles theorem. If your teacher needs you to write that out, here's what you'd have to write it out with. I'll actually write it out instead of saying theorem. By alternate interior angles are congruent when parallel lines are cut by a transversal. All right, that's the safe play. All right, now we can say that the triangles are similar. Let's see, what is it? DEF, similar to triangle BGF by the angle-angle triangle similarity postulate. Okay, done. Okay, 34. Now, describe the transformation that was performed. Let's see. So earlier on, we could tell it was a dilation, but of course, if you're describing it, you've got to be thorough. We want to get a center of dilation. We know it's a dilation, but what we need is specifics. All right, the specifics we're looking for are the center and scale factor. So let's go find those. All right, so if I had a straight edge, I would take my straight edge and I would connect, draw a line from B prime to B in both directions. Okay, I don't have a straight edge on this software, but what I can do is continue that slope. So what you're looking at is that's what we have there, that line. Now what I did that for was somewhere on that line is going to be the center of dilation. Somewhere. We don't know exactly where. Okay. I'm going to do the same thing with A and A prime. Yeah, it looks like down to left one. Oh, okay. So that helps. That is going to give us the center of dilation if we follow this path, and it happens to be, okay, I know right now that that's already the center of dilation because it's wherever two of the lines that connect the image and pre-image, it's wherever those two lines cross. Now, if we looked at C prime C, it'll have to do the same thing there. So we just found the center. The center happens to be 0, 0. The scale factor, I could do a number of different things here. I'm going to look at the easiest play here that I see. I'm going to count how far B prime C prime is and how far BC is. It's like 6 there. And I think I got 15 there, yeah. If I remember, that's correct, 15. So that's going to give me my scale factor. Now, the formula I use for every dilation problem, so I don't have to teach my students a bunch of different formulas, I just always use this. Okay, so then they just plug in what they know, and then they solve for whatever is missing. In this case, the pre-image, that's the original, is 6. We don't know the scale factor. We're solving for it. I call it K. I don't know why. That's just what I see a lot. So, and then the image is 15. Now to solve for K, we just divide, right? Inverse of multiply. And then 15 over 6, we can reduce that. Let's see, a 3 comes out of both. So 5 halves. You don't have to reduce it, but it's a little nicer. All right. So if I want to describe that transformation, I should be specific. Okay. A dilation centered at 0, 0 by a scale factor of 5 halves was performed on triangle ABC to produce triangle A prime, B prime, C prime. Okay, so that's a description right there. All right, and then the work shown to find the center and scale factor, that's going to start to accumulate some points. So you've gotten about 2 points there so far. Okay, all right, let me just get rid of this stuff underneath. Okay, so now we're going to explain, we're going to go back to this one, explain why those are similar. Well, that's going to be your other 1.5, 2 points, whatever's left. All right, so why are they similar? Well, it's not a rigid motion transformation that was performed. It's a similarity transformation that was performed. So I'm going to use that. So since a similarity transformation specifically dilation, was performed to map triangle ABC onto triangle A prime, B prime, C prime. The figures must be similar. It's that simple. It seems too easy, but that is exactly what we've got to say. Okay, you don't need a whole lot of other details. Just acknowledge it was a similarity transformation. That's kind of what they're looking for there. All right. So 35, okay. There's a lot of ways to do this. I could do a couple of congruent triangle proofs and use corresponding parts of congruent triangles are congruent. That, you could take that through and probably be safer. I just want to teach a little bit of parallelogram rhombus theorems while we're doing this problem. So it probably won't be used by as many people, but at least we're going through some concepts. So let me take you through that. I'm going to use parallelogram and rhombus properties to take you through this proof, right? I'm sure you can find a YouTube video, somebody else taking you through the congruent triangles. So let's start with this. First idea, it's a quadrilateral. They're not saying it's a parallelogram. But as soon as they said the diagonals bisected each other, it becomes a parallelogram. So I'm going to start with that. First, its diagonals, AC and BD, bisect each other. And that's given. Second major idea, because of that, ABCD is a parallelogram. Because when a quadrilateral has diagonals bisect each other, the quadrilateral is a parallelogram. All right, keep going here. Now, okay, so then this is going to take us to our next step. Angle 1 is congruent to angle 2, and that's because it's given again. And for the conclusion from that, we can say that AC bisects angle BAD by definition of angle bisector. It's actually the converse of. Usually we tell you it's a bisector. Converse just means, working it backwards from what we typically do. So now we have the congruent parts, and we're going to draw the conclusion that it must have bisected. So it's kind of working backwards. Okay, now ABCD steps up to, it upgrades up to a parallelogram. Because a parallelogram whose diagonal bisects an angle must be a rhombus. And that's one of our properties, so we can use that. All right, now we have a rhombus. So from that, we can get some progress towards what we're trying to prove. Okay, so why is ACD now isosceles? Well, the fact that it's a rhombus tells me that AD is congruent to DC. That's because the sides of a rhombus are congruent. All right, and then that takes care of, oh, sorry, I've got to actually say it. Let's create some more space here. All right, so that makes it isosceles because two sides are the same. So triangle ACD is isosceles because it has two sides that are congruent. All right, keep going. We want triangle AEB to be a right triangle. So we'll go with this. Let's see, AC is perpendicular to BD. That's because the diagonals of a rhombus are perpendicular. That gives us angle AEB is a right angle. Because perpendicular segments form right angles. And triangle AEB is a right triangle. Because it has a right angle. All right, I'll do the last one. I'm running out of time, so I'll do the last problem on the next video. Thanks so much.